Okay, so let us dive into the second half of chapter 22. So in this section, we're going to look at the difference between type 1 and type 2 errors, and also what are some of the tests of significance. When we have different groups or different interventions, what kind of tests do we use to look at differences between groups or differences between individuals? The book also touches on type 1 and type 2 errors, and this was always a hard one for me to grasp as a student. But basically, the idea is that every time we interpret statistical significance, if we reject the null hypothesis, we risk one type of error, and if we fail to reject it, we say, ooh, maybe there was a null hypothesis, there's a risk for a different type of error. So let me give you a quick example first. Let's say that you go to get tested for the flu. Now, if you got a false positive where the test says you have the flu, but you really don't, that's similar to a type 1 error. But if you took a flu test and it said you didn't have the flu, but you did, we would call that a false negative, which is equivalent to a type 2 error. So how does that actually look when it comes to our study? Well, similar to the flu test example, if you have a type 1 error, that's when you reject the null hypothesis. We conclude that we think there's an effect, but there isn't an effect, and the null hypothesis is true. So we're saying, ooh, something's happening, but it's really not. That's a false positive, just like the flu test. If you fail to reject the null hypothesis, you're like, yeah, I don't think so. I don't think there's an effect. I think chance played a bigger role, so I don't know if we can conclude there's an effect, but there was an effect, right? So you say you don't have the flu, but you do have it. So in a type 2 error, it's a false negative, right? Similar to the idea that you say, oh, they test you for the flu and you have it, but they say you don't. Well, a type 2 error is saying we conclude there's not an effect. We fail to reject the null hypothesis. We're like, we don't think there's an effect, but there actually is one and we missed it and we should have rejected the null hypothesis. That's that false negative. So I have a little graphic here. So if your null hypothesis is rejected, you think there's an effect and there was an effect. So if you have your null hypothesis and you reject it, you say, no, I think there is an effect, and there was an effect, that false, there's no error. It's a true positive. We say, we conclude there's an effect, and yes, there was an effect. But if we say, ooh, we think there was an effect and there wasn't one, that's that false positive. Or if the null hypothesis is not rejected and we say, ooh, we don't believe there was an effect. We're not going to reject the null hypothesis. We don't think there was an effect. Well, if there was an effect, so if we don't reject the null hypothesis, we say, yes, there was an effect and there actually was. So if we do not reject the null hypothesis, we say, hey, there's no effect. So if we do a null hypothesis and we say, there's not an effect and there isn't an effect, you can see true, no effect, then there's no error, right? That's a true negative. We're saying, nope, no effect, and there actually isn't one. But if we say, no, there's no effect, but there actually was, that's a false negative or a type 2 error. So hopefully this table helps a little bit when you're going through the chapter, because this can be a little bit complicated because we don't say accepting, we just say fail to reject. So you can get a false positive or a false negative. So how do we reduce type 1 and type 2 errors? Well, there's a couple different ones. One way that we can do it is you can change the statistical significance level. So if we go a little bit broader and we say, well, let's increase it to 0.10, we're okay with risking a little bit of chance. The challenge is then we increase the risk of a type 1 error. And if you remember, type 1 error is a false positive. So if we say, okay, we're okay with a little bit more risk due to chance, we could say, oh, look, this totally worked when it didn't really have an effect. But it decreases the risk of a type 2 error. But it opens up that significance level and it decreases the risk of a type 2 error. But it opens up that level of significance and decreases the type 2 error, right, which is a false negative, where we say nothing's happening, but there really is. So what we do is we go higher with their statistical level. We open ourselves up to a little bit of influence of chance, which can affect it. But if I go narrower and I say, no, I really want to make sure chance is not impacting the study, and I want to minimize the likelihood that chance is affecting it, we have this increased risk of type 2 where we say false negative. But when we get a smaller significance level and we say, nope, chance didn't play a role, we really want to minimize the role chance played, we do have an increased risk of type 2. We might say, oh, there's no effect at all when really there is that false negative. And so you can see when you go up and down on the statistical significance level, that's a challenge. We have to figure out how to fix that because either way we go, we're going to increase one type or decrease the other. Now, the way to decrease the risk of type 1 errors and decrease the risk of type 2 is we want to increase our sample size. When we get a larger sample, we're getting a bigger distribution of responses and we get less sampling error. And the bigger the sample, we can still have that lower statistical significance level of 0.05, which reduces type 1 errors, and it reduces type 2 errors, because type 2 errors are really vulnerable to extremes. If I have a sample of 20 people and some of them had really extreme answers, I may say, no, there wasn't an effect because everybody was so spread out, when maybe there actually was. So what we do to reduce both types is we need to decrease the significance level and increase the sample size. So finally, with this chapter, after they talk about probability and the role of chance, when we talk about type 2 errors and type 1 and we talk about effect size, we're going to look at tests of statistical significance. Now, the book doesn't linger a whole lot on these, depending. Some textbooks focus more, some less, but I do want to talk a little bit about these. Now, a few of these are extra information I'm throwing in. They're not going to be on a quiz, but it is still important to understand the tests mentioned in the book in that gray box. Now, when we're looking at tests of association, we can do chi-square. So remember we looked at those frequency tables where we broke it down by gender and if they had attended a parenting class? Well, the cool thing is there's actually a test that can say those breakdowns in those boxes, how likely was that due to chance and how likely was it due because it's representative of the larger population? And so we have actual tests that can say, was that statistically significant or not? We also have those correlation tests that we talked about, looking at that strength of association between two variables. We can use Pearson's R, Spearman Rho. Let's say the correlation is 0.7 and the statistical significance is 0.01. Yeah, we can say there is a correlation that is statistically significant. It's not just due to chance that there's a relationship between the two. We use a lot of t-tests. You'll see these quite a bit, especially when there's a pre-test, post-test for an intervention. T-tests are typically used when you have two groups of scores. So it could be two different groups of people, or it could be your score on a pre-test and a post-test. So there's a couple different types. We have paired samples where you're saying, I'm going to give the exact same group of people test 1 and the exact same group of people in test 2, and I'm going to compare participant A's score on test 1 to test 2. I want to see, did participant A have a statistically significant increase from the pre-test to post-test? Or you might have independent samples where you have two different groups, you do some sort of measurement, and then you compare the groups. Is there a statistically significant difference between the groups, or were they pretty similar? So let's use an example. Let's say that you have two groups of individuals. One group of individuals does a DEI training in a virtual, like through a virtual meeting, and one does a DEI training in person. And I want to see if there's a difference in scores on the exit survey. Let's say we are going to measure how they felt about the class on a Likert scale, strongly disagree to strongly agree, and we come up with a number. And we give that to both groups at the end of the training. We could eyeball it and say, oh, well, it looks like their scores on the exit test were pretty similar between the two groups. But this t-test actually shows us the p equals 0.94. That is not below 0.05. That is not below 0.1. So what that means is we can say, no, there was no statistically significant difference between the groups. And in this case, we use Hedges G. This is based on one of my studies, and I didn't have a nice parametric large sample. But Hedges G found 0.04, which is a teeny, basically not really an effect. So what we're saying is there's no statistically significant difference between the groups on their final scores. We could conclude maybe it doesn't matter if you do it virtually or in person, and there's not a strong effect size either. We also have a couple other ones. ANOVA is the analysis of variance, and that's used when we're looking at 3 or more groups. So that could be individuals who took a pre-test, a post-test, and a second post-test, or it could be 3 different groups. And then we have what's called a MANOVA, which is multiple ANOVA, where you're looking at multiple groups with multiple independent variables and or dependent variables. So here's an example of what that might look like. So let's say I'm doing this study and I want to see if there's a difference in the perceived stress scale scores between participants who were eligible for food assistance and received it, those who were eligible for food assistance and didn't receive it, as well as participants who were not eligible. I want to see if eligibility and receiving food stamps has an effect on your stress score. Well, maybe what I do with an ANOVA, because I'm looking at 3 or more groups, I am going to run those results. And what I might find in this hypothetical study is P is less than 0.05. I can say there was a statistically significant difference between groups based on their scores from the perceived stress scale. So I might be able to say, I can't tell from this exactly, but I wonder, it seems like there's a relationship between people receiving food assistance or not and their current level of stress. Finally, the book doesn't mention it, but a common one you'll see sometimes is linear regression or multiple linear regression, and that's simply used to predict outcomes. That's if we have a lot of data, and maybe we say, I think that I can predict the amount of years of education you have with your current income. And with a linear regression, I could pop in and say, okay, so I think if you have 3 years of college, I can predict you will make this amount of money. So when you go through your literature review, you're going to see examples probably of all of these different types of tests. Finally, the book references the idea of a meta-analysis. Because there are so many variables and because effect sizes and statistical significance levels change across studies, we can sometimes use a meta-analysis. This is really nice too if you have conflicting results to see when they're all pooled together, what do the results show? This is one of my favorite studies. It's a study where they were looking at the prevalence of drug and alcohol use disorders on individuals who had come into the prison system between 1966 and 2015. So tons and tons of data. What they did is they looked at all these different scores. They found 24 studies in that time period, representing a total of 18,000 prisoners across 10 countries. Then what they did is they pooled all the numbers together, and they came up with a pooled prevalence estimate of 24%. So that meant that with all those studies and all those countries and all those prisoners, they found that the estimate of alcohol use disorder was 24%. Using all this research, they were able to conclude that substance use disorders are highly prevalent in prisoners or those in the prison system. Approximately a quarter of newly incarcerated prisoners of both genders had alcohol use disorder, and the prevalence of drug use disorder was at least as high in men and higher in women. So meta-analysis is great. You can go through and say, oh, I really want to know about EMDR in children. See if you can find a meta-analysis pooling all the data to see if you get a bigger picture. The book obviously talks about reading this with some caution because sometimes meta-analyses are done by organizations that are being funded that way. Maybe they have a buy-in. So we really have to make sure that we're reading to make sure the methods are good, but meta-analyses are great and a really good starting place when you have a lot of conflicting studies. So there are all my references. Next chapter, chapter 23, is the last one, and it's a short one because it really just looks at finding funding and writing grant proposals and what that looks like. See you soon.